Okay, hello everyone. Today we have a seminar. It's more like a semi-internal seminar about evaluation of the data from Troitsky mass experiment with Kotlin and our libraries and Jupyter kernel. And we decided to make the seminar in English because every time somebody asks for some information, if it is in Russian, I have to translate. It's not convenient. So it's a seminar, so please ask questions during my talk. It's not a presentation. It's just I will just show you how things work. Ask questions, and you can ask questions in Russian if you want. I will translate for the record, and then I will answer. And please tell me if something is wrong with the sound or visibility or something like that. Let me begin at the beginning, and let me share the screen. Okay, first of all, about the experiment, about what we are applying these tools to. It's called Troitsky mass experiment. It's in Troitsk, near Moscow, and the experiment is for measuring. Initially, was made to measure electron neutrino mass. I don't think I have a lot of time to go into detail how it works, and most of people here probably know about it. But the idea is that we measure the electron spectrum from the neutrino, from the tritium decay, and here we have a spectrometer and electron pass through the spectrometer, and then registered here at the detector. And from the electron spectrum, we can get information about the neutrino mass and about existence of some additional particle like sterile neutrino. The final result of the first stage measuring with the electron neutrino was published in 2011, and it was the best result, the best limit on the sterile, on the electron neutrino mass, on the direct search for neutrino mass in the world until the last year, when the Kotlin experiment, which in Germany, got the better results. It's like our best result. It was actually my PhD thesis, the analysis. It was done not in Kotlin. Kotlin was not there in 2011. It was done in Java, and then it was done in Oberon black box language. It's one of the dialects of Oberon 2. It's called component Pascal. It was done by my supervisor Fyodor Tkachov, and then later it was rewritten in Java by myself. It was and last 10 years we were working on the sterile neutrino search, and still the sterile neutrino limits are at some regions, they are still the best in the world. Okay, Roland asked me about the collaboration. The collaboration is not very big right now. It's Troitsk, actually, Institute for Nuclear Research in Troitsk. It is MIPT right now. It is Max Planck Institute for Physics in Munich, which is a Tristan project we are working with, and some small collaborator from outside is Dubna, or Joint Institute for Nuclear Research, and some minor collaborators. This year we got increased funding for this project, so there are additional collaborators on the new types of measurement from Nizhny Novgorod and maybe other research organizations as well. And here, this site, it's not very good. I've made it myself, but it's still not very good from the point of view of you see Russian names on with English text. It's not very good. it was done for funding purposes, but still you can find it. It's a mass.ru.unu, which means in Russian it's a unique scientific setup. It's a transliteration from Russian. Lots of things here, and some nice pictures, the best result here, and the team, these guys are from Munich in the front. It's probably somebody know those guys, and that's all. That's a Russian team here. Okay, this is the how to call it, preamble, whatever. Now we are going to actual software, and first of all we need to understand how we store the data. Today's our task is to read the data we got in the primary detector and then process it with tools written in Kotlin. All tools were in Java, and we are slowly and in Kotlin as well, but we are using the new generation of tools right now, like Kmath. It's the first time I actually using it in real life. Dog fooding, like JetBrains wants to calls it. Plotly Kit, and the new reincarnation of the DataForge framework. I will talk about it later. So first of all, please tell me if the size is too small. But first of all, we want to see the data. Here I have some example data from different, and please do not hesitate to ask questions during my talk. I will understand if everyone understands anything or everything, or don't understand anything at all. Here are some samples from experimental runs from different years. It's 2017, 2018, and this is last year, 2020, in the December, right before the New Year holidays. Today, our work is to process some files from the last run and to understand some things about it. So I have here only the one directory measuring with a so-called electron gun. We can go back here, and the electron gun is here is the electron gun. It's placed in the backside of the tritium source. It hits through the whole setup, which is like 15 meters, and hits the detector. So it's a calibration source, and it's used for calibration. And our task is to see the spectra from those calibrations and make some estimations with them and check those amplitude spectra for anomalies. So here are the data. One of the interesting things we get in Troitsky mass, we did not use any. By the way, where is Vasily? Do we see? Vasily is not here. It's bad. Okay, we will show him the recording later. We decided not to use the database for storage because it's huge. It's like several terabytes of data, and it could be more. And we designed a very non-orthodox way to store the data. It's actually the file-based, you can call it the file-based document database if you want, but they're actually just files. You see, we have the structure here. We have this directory called diabaticity, which is the measurement of the gun measurement. Don't go into the detail of the term, it's historical. And here in this, we have several different directories with names equal to the potential on the gun. It's an electron energy escaping from the gun. And we have those directories for files with a gun and files with a gun turned off to subtract the background. And inside we have several scans with a potential on the electrode, and four sets here, 4 sets here, and inside those sets we have actual points. We have a set level metadata, which is actually just a, probably I should open it with the VS Code. It's a little bit, no, yeah. Here you see it's actually a JSON file. So it has some comment in Russian, and it has the other metadata like start time, the type of this file, the revision, and actually here is a link to the documentation about the format. This is very good invention, because when you forget how to read this thing, you can always go to the documentation and just read it. And this was everything here was done by Vasily Chernov. It's his work is primary. You can see also here is this binary, some kind of gibberish here. It's a binary tag on the top of the file. This binary tag is needed to separate the files used by our data acquisition system from other files. It's a little bit changed right now, but still the idea is the same. There should be a binary mark which explains that this file should be treated by the system. Also, you can see we see here also the scenario file, which says what different measurement points with the different times. It's a point with a high voltage of 14 kV, kilovolts is measured 10 seconds, and etc. for other points as well. We have a voltage readout. You also see, you can also open it in the VB scope. Also, there is a text file with the metadata, which also describes the format and the revision and the type. And we also have this binary tag. The binary tag serves two different purposes. One, I said, it explains that this file belongs to the data acquisition system. The second is it marks, it says what is the size of this metadata, human readable metadata header, and what is the size of this data block here. So each file is a so-called data fortune envelope, and it is it consists of two blocks. One is the human readable metadata, and the second is the data. And actual files, actual data files, probably okay. Actual data files, you can see the metadata is more, how to say it, more full, more detailed, and we have a binary, a lot of binary code here, which actually stores the data we acquired. Also some metadata here and format, and the data is stored using the protobuf encoding, which is maybe it's not the best storage format. I mean, from the point of view of speed, or compression, but we found but it is the most universal one, because you have a protobuf readers in any possible language. It simplifies things a lot, and I think it was a good solution. We also had experience with storing not the protobuf but zipped protobuf. If we want to get the storage capacity, we just zip this format and add just one field here in the metadata that the data inside the binary block is compressed, and it's automatically decompressed on read. Okay, so now we want to work with those files, and I go to the code, I have created this project. Let me collapse everything here. Probably switch to presentation mode.
Could you just tell us a few words about how those files get created? Just a
Yes,
few.
yes.
Sorry,
Actually,
what happened during the experiment? Yes, thank you.
yeah. Okay. So I probably will have to switch back here. I'm not sure I have any nice pictures on this page. No, no scheme here. Okay. Then let me tell you without figures because I will have to search for additional information otherwise. You see the decay or electron gun, it happens here in the source. And then electrons traverse here, and here is the spectrometer, and for different voltage, different so-called retarding potential here, we will have, we cut only the part of the spectrum with the energies above this potential. So what we do, and then on the detector, we measure all the electron with the energy above this potential. So the workflow is the following. We set the high voltage here. High voltage, I mean, few kilovolts. And then we measure like for 10 or 30 seconds and measure all the electrons which hit the detector. And for each electron, we record its time stamp and we record its amplitude, which is proportional to its energy. And then we have a lot of those electrons, and the systems, data acquisition systems here, it records all those electrons, compress them into blocks, adds the metadata, and sends them to the operator computer. In fact, it's more complicated than that, because you have to send the signal to the high voltage, set the high voltage, then get the signal that the high voltage is being set. Then you have to send the signal to the readout system, start reading, then get asynchronous messages about reading. So it's not one single block. You have also some messages about the process of the reading. Simultaneously, you also get the messages from the high voltage about years and about something else. And then you get the asynchronous result. And then you combine together the data from the detector and the data from the high voltage. So it is actually not so simple, not quite simple process, and it is described in details in Vasily Chernov's PhD work. I can send you the link later.
Thank you. And so the software which runs on the computer is a Java.
No. There were different iterations of the software. The first implementation was done in the C++, actually in Qt, because we had to have a user interface for that, embedded user interface. Then we understood that Qt may be not the best solution, and we wanted to try different things. And Vasily changed most of scripts which run in the readout and the high voltage to Python. And after that, it worked quite fine. But after that, we needed some online data processing, like zero suppression. We don't have time to go into detail. And we found that the Python, even with NumPy, is not fast enough. It's probably there are problems with the parallelization, and we Vasily rewrote some of these online processing algorithms to Kotlin, and it became much faster, like 20 times faster. Even the first one was in NumPy, but still writing in Kotlin. It's not because the Kotlin itself faster than NumPy. It's just because it was much easier to implement more complicated algorithms in Kotlin. So Now I believe Vasily is rewriting everything in Kotlin. He likes the language, and probably will be some parts in Python and some parts in Kotlin. It's fully asynchronous system, so it could be a polyglot. Okay, and the slow control. I'm not sure if you know what slow control is. It's a reading of this all other sensors, and like cryogenic magnets, etc., are done in Kotlin right now. A little bit of Java, and most of it is in Kotlin. Okay, going back to I have a app idea, so that's where is my panel? Where is my project window? I'm not sure why it's not showing. Oops. Okay. Oh, I can do it like that. In the EAP, it does not work for some reason. Okay. Alt 1. Okay, I will remember how it's not. That's a UK band. First of all, I need to show you the protobuf reader here. And for that, we have a simple plain old protobuf schema. Probably all of you are familiar with the protobuf schema. If you are not, please read about it. And here, everything is explained. We have a so-called point, which is the measurement, one single measurement with a fixed high voltage. Then we have a channel. They are not used mostly, but it was done for multi-channel detector. For example, the Tristan detector from the Max Planck Institute uses multi-channel read. And then inside channel, we have a block of data. And we have two different readout. I forgot the words. Regimes. We can read individual events. Individual event, it's just a pair of time and the amplitude. Actually, amplitude is not uint64. It's uint like, it's a short. It's a 2-byte. Unsigned integer, but since the protobuf doesn't bother with the actual sizes of numbers, Vasily decided to do it this way. So, and the time is just array of time, not from the beginning of the block. So it's the time relative to the beginning of the block, and the beginning of the block should be the time of the beginning of the block should be recorded in the point metadata. And another way to do another readout regime is the raw data frame, which is like a waveform. If you are listening to music, you can see the profile of this sound wave, and we can do the same. So we can separate those pulses in our readout system and record the amplitude of each pulse, or we can record this waveform and then separate those pulses programmatically. It consumes much more memory, because here you have only one number and here you have like several hundreds of them. But it allows us to do more complicated things like advanced pulse separations. Or again, you can consult with Vasily's PhD thesis about it. And then in a single block, we can have several frames, any number of frames in one block. And this one, I believe this one is not used right now. Length. And we can have these arrays of events of the same size. No, that's all. That's basically the whole structure. So we could have frames and we can have events, and we need to read everything. For that, I have this project here, which is called NumMass Data Model, which shows us the actual model of the data we will be working with. And let's start from the point downside, and then we go upside. Here we have a NumMass point, which could have, which has a metadata. Meta is comes from the DataForge framework, and it explains the tree of value tree. I do not have time to explain it in detail, but it's a value tree. It can store any it's type safe value tree actually. So it allows us to store primitives in a tree and then do operations with this tree, convert it to types and other things. But in the end, think of it as like a JSON tree, not necessarily JSON actually. But then we have blocks. If we go to the parent block, we see it was the latest change. We have this block class which describes its content. So each block has a start time, the length. We use a Kotlin XDateTime library here for multi-platform. You can see that all the definition is actually multi-platform. So we can use the same classes in the JavaScript, for example, or in native if we want. Then we have a flow of events. The flow means, probably you know what a flow is. It's a asynchronous flow. The good thing about flow is that we do not have to read any event before we need it. So we can conserve the memory. Remember that it's about few terabytes of data, so you can't load everything in the memory. It's actual big data here. And those APIs allow us to work to read only the data we actually need. And we also have the same API for frames. So we have frames here. Some additional classes to create those blocks, and I won't go into detail. You can see that the version is not this old, but the class I've taken as a base is like 3 years ago. And the event is contains just 2 numbers. So going back to block and going back to the parent block was invited because we want to work with blocks which contains other blocks inside. It's just a structure I use. It could be done differently, but it's convenient. And the point contains those blocks. And then we can create the channels by selecting only blocks with a given channel. So we group those blocks by channel and return map int block, where int is channel name. And here we combine all blocks with the same channel into the single block for easier processing. Then we have some additional default implementations for values, because we want to know the high voltage for this point. We want to know the index during the set of this point, and some additional things. Like, for example, we want easy access to all events in the blocks. These things should be actually moved to extensions. I can do it right now. I can't because it's override. Okay, those things actually should be moved if it was not the part of the interface, we should move those things to the extension because they do not use the internal properties of this class. And so in Kotlin, it's good to move those things to extensions. Now we have blocks, frames, and we have a NUMAS set. NUMAS set is the directory in this, which contains an ordered list of points. And it has a start time, and mostly that's all. Some utility methods to integrate it into the data forge, but mostly it's just a ordered list of NUMAS point. Now let's go to implementation. Here we have only APIs, basic APIs, but we do not have any actual reading. And we go to this to build first. Here I first used Google Protobuf for this, but last week I decided to try something new, and I replaced it with another Protobuf implementation called Wire from Square. Square is the name of the company. And it's much more simple in the configuration, so we just have to set this up and this wire, and it automatically finds this source set, the proto, and it generates let me show you. It generates the files for this protobuf for this protobuf scheme. It's huge. No, not so huge. It's 600 lines. The Google Protobuf was about like 3,000 lines, so it's small in comparison to the Google. And we have not this one, this one, and we have this implementation of NUMAS point, which is just reads this protobuf. It takes a builder of this protobuf point and derives all those blocks and data from it. And it's more or less simple, with the one exception. When we want to read the file, the envelope is the format. It's a data forge format which includes this meta header and the binary block. And the only complication is that we use additional layer here because we want to include the compression. We read the data stream as a simple data stream, if it is simple, but if we have a flag saying that it is compressed, it actually deflates the zlib compressed file on the fly. Okay, now we have this point, and we have this everything else, and we have also we have this additional set built on the directory. In order to read the directory, we need two things. We need the data forge context, which stores all information about the execution and works as a dependency injection route in data forge. And we need just a Java Neo path to work. This is the whole project, which this is data proto. It's a Kotlin JVM project. So here we can't work with files in common, but we can work with files in JVM. If we want to work with files everywhere else, we need to provide all different implementations for different platforms. So now we have those points. There is a controversial point here because we are loading them, lazily loading them and saving them into memory. Maybe it's not the best way. Maybe it's better to load them each time we request those points, but it could be decided later. We will have just to remove this lazy, and they will be read each time we request them. And this directory-based data set, path-based set, also has a list of high voltage data inside, and it also is read from file. You can see this nice new Kotlin syntax to work with the paths. It was included in the latest release here. This is actually an overload operation. So now we have everything we need to work with files, and I've spent a lot of time on it. Let's go to actual implementation of things we need to do to analyze them. And for that, I've created additional project, and this project called the workspace. Let's see how it works. You can see that several files with a small letter. We have now it's not an official, but it's a convenient naming convention that files that do not actually have a primary class are named with a small letter. In Java, you can do that, but in Kotlin, you can name files with a small letter, and it's convenient. So let's see first how we work with the amplitude spectrum. The amplitude, sorry. Probably need to add the new mouse. Here we have some extensions. For example, I want to create a spectrum, a histogram of event amplitudes, an amplitude spectrum from a new mass point. For this, I create an extension. I do not create a new class, everything right now. I just create an extension, and here I actually use a kmath. You can see, yes, I finally use the kmath. And we use a small, it's more or less in prototype stage, a module for histograms. And I just create this histogram with a given bin size and the sorry, maybe I should. Oh, will it work? No, it doesn't work. Okay. So those bins just have a center. The first bin starts at 0, and the bin size is 1. So we want to get all events in the single bin. And we just collect events, the amplitude from each point, and put it into the histogram. Put is the method of the histogram builder here. So it puts just one event. And we need run blocking here. Who knows why do we need run blocking? Nobody knows? Are anybody live here? Nobody knows. Okay. We need this part because the flow we use here is asynchronous, and in Kotlin, to collect the asynchronous flow, I need, it's a suspended function, so I need run it in the suspended context, and for that I need run blocking. But okay, it's not for physicists, it's for programmers. Then I also create this operation. I won't talk about it right now, but it will be useful later. So, and then I can also collect a spectrum from a number, merge the spectrum of several new mass points with the same voltage. I explicitly check that all of those points have the same voltage and give a warning if it's not. And I have a very simple reshape function which changes the binning of existing histogram, because we probably will want to change the binning a lot of times without rereading the whole data. So we want to store it, the histogram, with a binning of 1, and then reduce the size of bins from, not from the initial data, but from this histogram. Then we have some why is it okay? Just changed recently. Then we read the directory, and we read it as a data tree, which is also a data forge construct. Doesn't really matter. What important is that in the end we have a tree or tree-like structure of this new mass directory set. And also in future, we can also add an ability to automatically update this tree when the files changes on the disk. It's sometimes useful when you trying to interpret the data during the experiment. Then I have another file here which uses some extensions for plotting those things in the Plotly kit, of course. And we want to create traces from spectrum. We want to create plot this shapes, so there's histograms, and we want to plot the high voltage data. I remind you that everything here is extension. It's not no new classes. I'm just adding new functions to those classes. And here I also add these to the Plotly. Plotly is the object inside Plotly kit. It doesn't serve any other reason. It's just an attachment point to attach such things, and it is not used. It is not used here. I use it only because I do not want to place these functions in the global namespace. It will be hard to find it. I will show you right now. And probably that's all. It's utility. I'm just loading these. I also have here this dependency injection in order to read these binary marks, because they are obsolete. Dataforge now does not use these this syntax for binary mark anymore. Finally, that's all. The preparations is done, and now we can go to actual reading the data. That's all. 2 lines here. To read the data, I need to draw 2 lines. Let me start it, and then we will see, and then I explain what happens here. It should recompile because I changed the source code a bit, and here we are. Now we have the spectra, and you can see that I have the spectra of file with this path, and I have a lot of points here. It's a Plotly, so I can turn off everything. Just turn off everything, please. And then I can show the spectrum for 1 point. And we see the generator here. It's just consistency check. And here's some kind of spectrum here. Nothing to see, actually, because probably this is file without data. And some background. And also I can see the plot of high voltage in time. It's you can see this April 2018, and we see how the high voltage change in time. Those jumps to the monitor point, and those are measurements. Brilliant, and we can save the picture if we want. Just turn it on, turn it on, and save it as a picture and place it in the article. Yeah, we can then use it in the article. Okay. Now it's the wrong project. Now let me explain what happens here, why it's so short. First of all, we use the method I've already shown you in the and read the specific directory with the specific path, absolute path. And then I remind you this is a data tree. I can specify type explicitly, and this is the data tree. And then I request a branch of this tree with this name. I think it should work without. Oh, it won't. No, probably will have to add this method later. But I can request. It should work. Well, why it does not? I forgot to add the import. Yeah, now it works. Okay. It's an extension function, so I have to add an import for it to work. And I request the branch, and it's lazy, so I have to add await. It's a suspended function. Or throw an error if I did not find it. And then I use this plotly extension to draw a plot, and you can see that here I actually use HTML inside this plot. This is how Plotly-Kit works. I can add HTML, I can add plots in any other information here. I just can use the full HTML markup here, and it will generate appropriate HTML page with the cycles, with everything you want here. It's quite convenient. Actually, I did not ever expect it will be so good. I was thinking it's a side project here. Now let us try to actually read. We do not have a lot of time, so let us try to actually read the actual data we want to work right now. For that, I am creating. I am creating. I can use the worksheet mode. There is a so-called worksheet mode, and I can do that. I'm not sure it's a good idea. Let us keep. It will work, but there are suspended functions here. So for me, it's more easy to work with the regular files. So we create a file at the main function here. Then we go to my file manager, and we want to enter the actual root path of the run here. So I'm taking this. I am adding the name. And it's red because I did not end this suspend. Okay, now I have the data tree, and now I want, for example, I want to see all files here. And for that, I say flow collects oops, what happened? What happens? I think I know why it doesn't work. No, it does not work for some. Maybe something wrong with the. Not sure. I really don't know what happens here. Let us try to switch back to. And this one works. I'm not sure why. So let's see this, and I will later check why the actual one does not work. You see, I just printed all the metadata from different files, and I can say, for example, print not the metadata, but print its name And now I have a name on top of each metadata. And then I can select data. For example, I can filter like data. Start speed. Here, I'm just filtering the data, and should probably no, it doesn't work again. Okay, there are a lot of things we need to. A lot of things, small things here that are not tested. Yeah, something's broken in the. Okay. I forget. I erased the actual thing I wanted to do this. So I need again REPL flow collect print. Yeah, no, it's actually working. So you. No, it's not. No. Here we are. So I filtered only the data sets acquired by Vasily himself. I can do the same with the dates, and I can see, or I can see like, I can also do some other things, filtering by meta. I can't, I probably should not go into the data itself because it's lazy here, but it still works. Now, since I've spent a lot of time discussing technicalities, I promised the Jupyter. So I will move to the Jupyter, and if you have questions, we will discuss it later on we will have an additional session. Now, the problem is here I use a lot of my development versions of my library. For example, you can see this Plotly version is dev 5. I do not think it's published. Kmath version is dev 6. It's not published, definitely. And the DataForge itself is version dev 3 is not published. So I want to keep it simple. I want to, for people who will use it, and I want to, for them not to bother with the building and building all those dependencies with the correct versions, etc., etc. I want them to just do simple things like they do in the Python. For that, I'm just bundling all my files into one jar file via the shadow plugin. You can read about this. It's a shadow plugin, and all I need to do is to run a here we are. All I need to do is to run this shadow jar task. It compiles and takes all the dependencies I need locally, and it's create the shadow jar. The shadow jar is located in the build directory, and I can go there now. Here we are, and here is the build directory, and here I have this. It should be here. Why it's not here? Let me check. What happens? Aha! Yeah, it is. Everything is correct. It's not called shadow. It's called all. You see this file is large. It's 13 megabytes. It includes all the libraries, everything we need to run this. And then I go to my data directory, and you see I have this notebooks directory here, and I just copy this file and overwrite existing file. And now I want to start the Jupyter. I go to the console, Jupyter lab. And in Jupyter, you actually can, in Kotlin Jupyter, you can load local jar files. What do you do? Please start the Jupyter. I don't know what it does. Since it's thinking about something, oh, yes, it started. So now we are in the Jupyter, this picture. And I have a very small Jupyter. I can probably turn off. We'll see later. So in Kotlin Jupyter, it's this file is located here in the same directory. And in Kotlin Jupyter, I can load external files by just using file depends. Let me just depends on, and here I just need to put the name of the file I want to add in this jar, and it should just work. Oops. And you see something happening, and it's done. And now I can check if everything is ported correctly. And for that, I get import rule dot. And yes, I have the package on the class path. And for example, I can find functions. And for example, I can do it like this. And I can do it like. Okay. Questions right now? I need additional input for coroutines.
Do they plan to integrate Jupyter with IntelliJ?
Yes, yes. There is a plan. There is a so-called scientific tools for IntelliJ. It currently supports the Python very nicely, and they are working on providing the same support for the Jupyter. It's not ready yet, but they are working on it. And it will be really nice because it will allow us to display those HTML as well as swing forms in Jupyter. It's very good. We're looking forward. And you can see that I just run the function and I get the separate file. It's stored here in my temporary directory, and it just works. But it's not quite convenient to do it this way. I need all the imports, and I need to open files in the separate page, which is not convenient. So in order to avoid everything here, we use another mechanism in the Kotlin Jupyter, which allows us to create module descriptors. You can read it on the Kotlin Jupyter page. Maybe I can just open it. Here you are. You see this those description of views and different libraries, and we have old versions of Kmath and Plotly-Kit here, and other libraries as well, and Kotlin for deep learning and deep learning for G, a lot of libraries, and you can easily add your own. And in the near future, it will be also possible to provide the descriptor inside your library. So you're loading it, and it will just work without. It will just take the descriptor from your jar file, but it's not ready yet. And for this, I provide the descriptor. and I probably can open it right here. The descriptor provides better accessibility to functions you want. For example, it adds automatic imports. You do not have to write imports for those classes. They will be by default imported in each cell. You do not have to provide repositories if you load. You can load artifacts from a Maven, from the Gradle. And what is more important, there are things called renderers. So you can automatically render the results of the cells in the like the following. So you do not have to write each time, render me something and wrap it in HTML. It could be done automatically. It's a very important thing. But there are also a lot of other things in Jupyter kernel. For example, it is possible to do a staged compilation in Jupyter kernel, but it's beyond the scope of today's meeting. Now, I've created this simple thing. Most of them are included or in KMap or in the Plotly kit descriptors already. But since I used custom bundled versions, I decided to duplicate them as well and merge the descriptors into one and use this descriptor, and it actually loads the local file. I can easily replace it here by the remote file. And now that I've loaded this thing, you see then some experiment glitches. Yes, it's experimental. Now I load my local classes and do the same thing I did with the idea, and I read the data, and I can see the actual meta of the data, and I can use the function, the same function we used previously. What happens? Aha, I renamed it. Okay, so now we need to write the mass directory, and here it's in the mass set. Okay, works perfectly. So now we have this page inside our notebook, and we can do we can operate these things. I don't have a lot of time, but maybe I will just show you, and I'm not sure why reading the data from there to from this directory does not work. So let me try it. Let us take some specific file just to be sure. Oops. Okay. I can't leave those things because it's not friendly to. Okay, and I see. So the problem is that something changes in the data format since then. You can see there is an actual year here, and I will have to look into it because probably something changed in the format, and we can't just read it. I will have to check with Vasily and see if something is wrong. But the old reader worked fine with the new files. Something worked. So for now, I will just leave it here. What I wanted to do is to select a single point. and I like there is a point to the index, the voltage, and I wanted to spectrum. Here I have a histogram, and finally I want to see to operate with the numbers. For example, I want 0.4 and 0.75. And now I want to operate somehow on the values of this point. For that, I'm doing. Let me do it then, and I'll explain what I've done. Channels. As you see, autocomplete works fine, and now I can see what happened. What is the channel for? Oops. I did not overwrite the string for it. So you see that we have, it's similar to what you have in Python for tuples. Kotlin doesn't have tuples. So these things called the destructuring declaration, and it's just a sugar for declaring two variables. You can see probably here. Here I've done those two extensions just to be able to use the structure declaration. And for example, I want to do operations on those things. For that, I'm not sure it will work, but it should. Okay. Should be the real buffer, but I need to add import. Import case size math real. Should work. What? I see. The problem is I have different sizes of the spectrum, but it's not quite easy to work with it. Maybe if we take another. No, it doesn't work. So the thing is that if I can't jump here, but KMUF by itself does not allow us to operate on the arrays or buffers in this case. But there is a nice project here made by Peter Kleby here and inspired by Thomas Nield, which adds a number of extension functions over real buffers. For example, here is a real vector. We have some real vector is just alias for real buffer or real point. It says all of those are the same type, and there are operations here on those real vectors. Now the problem is that we do not have those vectors with the same size. So the problem is that this histogrammator is not completely reliable in this case, because if some value in the bin is missing, it will just skip this bin completely. So the number of bins are not the same and they can operate. But if we change the function a bit, it will be simple. Of course, it's not quite convenient to add new functionality here in Jupyter, so I will have to go back to the project here, add more appropriate extensions here. For example, in the spectrum, I will guarantee that the number of bins is always the same. I will need to check the API for that. And then I do it again. I create this jar and I go to the Jupyter and I just replace the jar and restart the kernel and it should work. So the development cycles like that. But of course, for me, it's much more simple to work in the idea when I can have a lot of things like seeing the source code of the function, for example, which is very important. Okay, we're out of time, so please ask questions if you have those. And if you have them later, please write to me in Kotlin Slack, on Telegram, or our laboratory Slack. But it's better to use Kotlin Slack, of course. Okay, no questions right now. Probably it would be bad. It would be easier to do things in Python because Python is just done a lot of ready solutions for those things. But of course, it is the case if we are not doing actual development, because, for example, writing all these structures and lazy loading of data in Python, it's really complicated. It's possible, but it takes much more time and much more effort to do it properly in Python. So my idea and the idea of people in Kotlin for data group is to add new instruments in Kotlin and make it possible to combine actual development and data wrangling in the same language without switching between them.
Maybe you can tell us a few words of a few thoughts of yours around, maybe for people interested in particle simulations. What kind of project can they do using that data that you collect?
We've done some simulations in Kotlin for this project. It's a recent article. It's about electron operation. It's not published yet, but it's on the available in our archive. It's not for detector data. It's for the tritium source, the trapping of the particles of the electrons in the tritium source. The simulation for Troitsky mass is complicated because we are working in the so-called low energy physics. It's the energy of the tritium decay is like 18 kilo electron volts. It's low energy physics, and standard algorithms like standard programs like GANT do not work in this region well. So mostly we have to write all the simulations ourselves, and there is a simulation of electron trapping. There are simulations for ion transport in the spectrometer. They are not written in Kotlin. We use standard packages like CMion, whatever it's called. There are also a lot of grid simulations for electric fields and magnetic fields. And also there are some simple geometric simulations done for kinematics of the decays. But it's very simple from the physical point of view. There are no complicated processes there. But of course, we always need to be careful to make it fast, because we have a lot of, we need, for example, these electron trapping simulations, it uses like 10 million particles in a few minutes. For Giant, it will take like a week or something like that. And we need very large statistics because we need we study rare processes here with a probability like 10 to the minus fourth or something like that. So in the end, we have to write all the software ourselves.
Thank you.
Okay, we are completely out of time. I didn't expect it to take so long, but I hope that maybe you did not understand everything, but at least I hope you have questions and you will ask them later. The idea is to make you ask new questions. Well, then see you again. If you have questions, or if you have requests about some kind of discussing any other topic, please contact me and we will do that.